results after these two general lectures. Anyway, allow me, before going into my presentation, 5 minutes to propose the location of next meeting 1 year from now. We are in Syracuse. Syracuse is a very famous city, the mainland of Archimedes. So, we will be, Syracuse is composed by a mainland, which was the densely populated area in Greek time. Now is the main part of the city is in this small island. And the conference will be where the arrow is, just the tip of the island. And so Syracuse is a very attractive city. A lot of Greek remainings. There's a 3,000 seats Greek theater still in use. Baroque, medieval medieval city. The cathedral is built on top of the Athena temple. So the columns of the Athena temple are part of the cathedral. There is some painting by Caravaggio in the same square. And we will stay in that building, which is circled in red, near the Frederick II Castle. And this would be the hall for the main conferences. That will be the building with all the windows giving on the sea, but of course window will be closed during the conference, so no one will be distracted. And so this is some part of what you can see from this place. This is this structure. This is near to the Faculty of Architecture, so we will skip from one place to the other one. The structure is a naturalistic area whose honorary president is the daughter of Enzo Maiorca, might be somebody of you knows. He was a very famous diver who died some years ago. Okay, so let's go to some more mechanical stuff. First of all, I have to say this is ongoing investigation. So I'm just presenting some idea, some development, and problems, mostly problems. So this is the outline. So we want to, of course, work with architected material. We know why. There are many applications, so we have already seen that. And a huge amount of metamaterials have been proposed. Here is some foams, some lattice material. We know that they have very nice properties, for instance, for impacts. They have very large ductility, and so on and so on. So why we don't like, why not always they can be used? First of all, there's a general problem. This reduction of the stiffness is much greater than the reduction of weight, usually. There's a limit, of course. In almost all this material, we have localized damage development. There's a competition with the local and global damage. Sometimes this is desirable, sometimes it is not desirable, depends on what is the application. And there are manufacturing issues. In order to show that, I will present a small experiment. We produce this sample. The sample is made by titanium, is a network, so it's a lattice made by cubic cells. During the manufactures in the joint were posed some spheres so that we can have an improvement of properties in the nodes. And so we did some simulations.
and the simulation, extension, and compression. The simulation, we could develop rather large deformation due to the fact that the plasticity will spread almost throughout the whole specimen before getting to rupture. So in this image, the red spots are plastic areas. Okay, this can be seen in some detail. So the plastic was spreading, of course, at the joint. Those are rigid joints. Similarly in compression. Compression, the deformation shows some bands due to the boundary condition, which were clamped. And on top is what the analytical prediction we were expecting. On the bottom was the experiment. So completely different. And also the level we reached was much lower than the one we expected. The reason is that the sample behaved in a completely brittle way. So you see, it's very interesting because if the first look you can see the bands, 45-degree band seems a ductile rupture, but the rupture of the single microbeam was totally brittle. And the reason is that the thickness of this microbeam was small, I remember by fraction of a millimeter, so it's comparable with the grain size of the 3D printing process, and they've been much more fragile than what we expected from the properties of the titanium. So the idea is to switch from lattice microstructure to continuous microstructure made by surface shells. So foam is a possibility, but foams cannot be architected, so the process is random, so it can be nice. So we start trying to see what can be done with triply periodical minimal surfaces. Yeah, everybody knows what is minimal surfaces. Minimal surface is a surface that in each point has a zero mean curvature, so it's the anticlastic surface. These, from a mechanical point of view, has some benefit in the prevention of buckling. Other properties of the minimal surface is that locally, the surface is a critical point of the area functional. In some cases, a global minimum, so it is also interesting for minimizing weight. And also, surface is in equilibrium with an isotropic substrate of stress, which is very interesting from a mechanical point of view. What we expect is that using minimal surfaces, if the deformation is not very large, so we are close to the shape, some load can be carried out mainly by membrane forces rather than bending forces. So what we hope to achieve in this way is less brittle elements, versatility of design. I will show that. Then there are some other properties that are very interesting with this kind of structures. Triple periodic minimum structure divides, so that's continuous structure. They divide the space into not interconnected parts. That is very useful when you want to have fluid transport. Have been proposed some coolers made with this kind of design, and they can be useful in medical devices also. We can create hierarchical porous microstructures also, optimizing density and morphology. Another thing, which is actually probably why people started to investigate about this stuff, they are found in nature. For instance, in that butterfly, which has a very strange name, I don't know what its name, the wings are made by layers of gyroid. These are because they are photonic crystals, and they are used to give the bright colors in the wings. And also the beetles have some microstructure made by diamond periodical microstructures. This is not a new topic. There are hundreds of publications on this topic by now. People have tried to investigate, develop every kind of structure made by these materials. So I will make something I say now is pretty known, something maybe a little bit new, but anyway. Basically, triple semiotic minimal surfaces refer to Schwarz minimal surfaces. It's a family of surfaces developed by Schwarz. These are the most famous, the primitive, the diamond, the gyroid, the navies. I will not talk about navies, I will use the other three. In every 3D printing apparatus, there are already built-in software for building these surfaces, which are very, very famous. They use this kind of equation. This kind of equation is some general equation with some terms, and the level parameter, the t parameter. Actually, if this t parameter is 0, we get something which is, let's say a minimal surface between commas, and I would say y. If this t parameter is not 0, we get other things which are not minimal surface. So this is important. Wait. So this is, for instance, for the gyroid. What happens if this t parameter goes from -1 to +1? You can see better in the bottom line. When this parameter is very large, you get almost lattice-like material. So you can changing this parameter, modulate from lattice to surface. Anyway, we have to be careful because even with we set this 0 level, the level parameter to 0, we do not get exactly a minimal surface. This is shown the area functional in the red is for some mesh course, because we're measuring it on a mesh, for a discretized mesh. The red line is the one we get with the equation, and the blue line is one that we get from our form finding variational method, which is not exactly, so it's somewhat different. Not so much, but anyway, it makes some difference. So it should be, it is possible to take the minimal surface and change it in STL format and use it as a printing. Additional thing we can find in nature, usually these structures are not homogeneous. So they are combined in a hierarchical way. So they combine and with also multi-level hierarchical. So there are three ways we can grade these metamaterials. We can grade the thickness, we can hybridize the structure, and we can change the cell. So this is hybridization. So we start from, what is this? We prepare from alloy and diamond, and we go to a gyroid. This is a continuum transition. Surprisingly enough, in every point of the transition, mean curvature is 0. So it is, okay. I was surprised to find this, but this is, so it's a minimal surface that continually changes from one shape to another one. And that can be done with all kinds of Schwarz surfaces. This is in this case which are changing thickness. Thickness is a little bit more difficult. This is a continuous change of thickness. That means in the single cell, thickness is not constant, of course. And this is just changing the dimension of the cells. So starting from square and then elongating in one or two directions. So the idea is to control, modulate the hierarchical design by assigning some porosity function. This is defined by the user, and realize this porosity continuously controlling the size of the cells or other properties, right? And everything will be described with B-spline interpolation. Why? Because the idea is that we can use the same environment for doing CAD, optimization, and mechanical simulation. So we use isogeometric analysis, which is spline. So with the same environment, we can try to model everything. So the idea is we start from something, so a structure, this is a square in this case, we divide it in some certain number of cells. That's where the target of our realization. We have some distribution of porosity we want to realize, or density, or something else. We interpolate it with NURBS or spline, and so we assign it to come out with a continuous variation of the cell dimension that can be. And then, of course, if we increase the density of cells, we have better approximations. This is an example. This is just too crazy distribution of porosity in two directions. That's what we get, and the colors represent the red is the purple is the larger porosity, and the yellow is the lower porosity. It's just relative porosity. This is a 3D realization of this example. In this case, the microstructure is made with primitive cells, and in this case, this is the tail, and in this case with gyroid microcells. Now, imagine we want to make a mechanical analysis on this structure. We need some 6-7 million elements to make a reasonable interpolation of this surface, which means a very, very heavy task, especially if you want to make nonlinear mechanical analysis. So the idea is to use asymptotic homogenization, obviously, with periodic boundary condition to obtain the homogenized properties with standard. Yeah, it is very standard, and so what we did, and I will show some results of this homogenization. This case, this is the Young modulus. By the way, either the primitive and the gyroid, which are the surface I will talk about, behave in a cubic way, so they're isotropic. So this is the Young modulus as a function of thickness. It is interesting to see that there is a linear variation. Increasing thickness, stiffness increases linearly. That means that as we expected, the deformation behavior is membrane dominated. Otherwise, we should have found a cubic dependency on thickness. So it's very, very interesting. Poisson ratio is not exactly constant. Poisson ratio, and what is interesting is that the shear modulus almost respects complete isotropic behavior, almost, not exactly. Probably is due to the numerical approximation. Okay, this is it's a graph showing the Young modulus of the primitive gyroid, the diamond, is a function of relative density. So this diamond appears to be the stiffest microcell. Anyway, so that's of course they are done for the same kind of thickness, but we are grading, so single homogenization is not enough. We have to investigate all kind of possibility. So there's all this kind of elongated cells. So we have to do extension in either one or other direction, shear in one or other plane. So we have to make all this investigation, and so we come out with a bunch of results. This is interesting. For instance, the red on the left is the red curve is the modulus in the direction of where the cell is elongated, and the blue is in the other direction. You can see that as the cell becomes more and more elongated, it becomes stiffer. Why? Okay, if you look on the top, this is a very shallow one. So in this case, we have elongating in one direction is dominated by bending. If you go to the one which is more elongated, it's almost a truss, so it's called stiffer. So if everything seems to be nice. In these cases, I didn't expect
I didn't hope at least, the dependency of the Young modulus on thickness is not linear. So it means that bending now becomes more important, of course. And and this is the comparison. The red line is the isotropic cell, and the blue line is not isotropic cell. And then we have to do all this kind of also combination of the dimension of the cells. And this is everything linear. So everything has to be done in non-linear case of the way. Okay, so these are some results I've already said. So the homogenization is a function of the aspect ratio, the thickness, the morphology. So we have very many data. Okay, this is. So now, just to see if this can be useful for something, I present a case study. This is an implant, hip implant. It's used for femur fractures. So it is a kind of implant that is used to join the bone. The design has been almost standardized. Somebody had already proposed this in 2020 to use microstructure for doing this kind of analysis. Why? Well, the idea is that there is two parts in this implant. So the top part is the one is connected to the ball, is stiff because the part that is going to be inserted in the bone. The lower part is to be quite flexible because it has to adapt to what to the structure of the bone, which is the safe part of the bone, and also has to be kind of porous because we want that osteocyte can be introduced and reconstruct the continuity. Okay. So this is the design we are proposing. On the bottom there is it's a real implant used in surgery, and we propose this kind of design made by two parts. In this case, we use primitive as unit cells. The top part is much denser, which is the part has to be stiff, and the lower part has a graded porosity, increasing toward the bottom. Okay, yeah, okay. You can see now two enlargement of these two parts, and also in the thickness, porosity is increasing toward the center. To the center, we have almost a channel where fluid can flow through. Okay, these are images. Okay, so what's the idea is to need some detailed analysis, linear analysis, of course, in order to see if at least the idea of this could work. This is a shot of the mesh. There are 2 millions, not 2,000, 2 millions and something elements, some 10 million degrees of freedom. Anyway, could be done. I apply the shear force at the bottom. Okay, this is the deformation we get. This is, something nice. We want something flexible at the bottom. Unfortunately, I'm sorry, but there was an incident. I didn't bring with me the result of the distribution of stresses. However, it was almost impossible to understand them, so it's better to tell you what happened. That the bottom was almost very small stresses, of course, was we expected. There were larger stresses in the part which is built in, and what happened is that the order of magnitude of the membrane stresses was 5-6 times the order of magnitude of bending stresses. Yeah, you have to believe me, but so it's what we wanted to realize. Even though
And so this is, we used every cell was made with a primitive geometry. Okay, so this is where we have arrived. This is what we are investigated, but there are future developments. We want to make other kind of design, but we have a lot of problems. First, we did linear homogenization. We have to make non-linear shell homogenization, which has to be numerically based. We want to investigate local versus global damage. There is a big problem of contact. When we get very large information, they can be contact. In this case, any surface can contact another one. We have to apply the optimization algorithm for porosity with some objective function, of course. This is just application, there's nothing new. Now there's a problem with numerical analysis. Because we said we have developed homogenization, even in the linear case, and we have that. Now we want to make linear analysis on an equivalent continuum. But it's a non-standard equivalent continuum, because in each point we have different properties. So how can this be treated, especially in nonlinear range, in an efficient way? Maybe data-driven analysis. So we are a very small group, very, very small. So everybody who is interested and want to cooperate is more than welcome. Okay, thank you.
Thank you, Professor.